Thank you for meeting with me, Nitesh. I really appreciate it. Maybe we could talk a little bit about the new 3.3 kilovolts release.
Yeah, thank you, Aalyia. So again, good morning from PCIM here at the Microchip booth.
Yeah.
So we released our 3.3 kilovolt modules just last week in time for PCIM.
Yeah.
So 3.3 kilovolt module is in a 62 millimeter footprint, expanding our portfolio within the 62 millimeter all the way from 700 now to 3.3.
Yeah.
Now the beauty of this is customers can have systems that range in the voltage, but also the power levels because of the higher voltage we offer with the 3.3.
Yeah.
Now, to achieve the 3.3 in the 62 millimeter platform, we had to do a couple things. We had to increase the isolation voltage. The standard for 62 millimeter is about 4 kilovolt. We had to achieve 6 kilovolt. The other thing we had to do was increase the creepage clearance distances. So we added certain ribs to increase the creepage to 23 millimeters.
I see.
And we also had to go to a CTI 600 case.
Yeah.
Now, we had to do all of this because we had to fill a gap in the market. So the gap between what we had available in the discrete to the really high power was quite evident.
Yeah.
And we filled that with the 62 millimeter. The application areas for the 62 millimeter is, it could be traction, like heavy duty vehicles for mining equipment or buses or trains, auxiliary power units, but more recently, AI data centers. So AI data centers require front end, where you have the grid voltage that needs to be converted down to a DC voltage for use within the data center. And the 3.3 kilovolt devices are used in what is called as an SST, or a solid state transformer, where you have the high voltage grid coming in, and you have that conversion to the low voltage through the SST.
Gotcha. Thank you. So I know that the previous pack was the BZ pack, and that uses the standard silicon gel potting, but this one uses silicon nitride.
Correct.
And so you talked about the extended creepage distances, and do you mind talking about the design innovations in this this module in more detail?
So the BZ pack, as you mentioned, is a standard industrial module, which requires a couple things. One, low cost, but also decent enough reliability and thermal impedance. So with that, we use an aluminum oxide, which provides the lowest or the best trade-off between cost and the reliability requirements from a customer standpoint and the thermal requirements from a customer design standpoint. But to achieve the same things with the 62 millimeter and the 3.3, we had to go to a silicon nitride. Now, going to silicon nitride from an aluminum oxide allows you to do two things. One, it gives you great thermals because the thermal impedance is much better with silicon nitride, but also extended power cycling. So power cycling is a term used where every cycle of on and off, you increase and decrease the temperatures within the module. So your components within the module see the dips and lows, in the highs and the lows, right? So that impacts the reliability of the module. So going to a silicon nitride substrate allows you to excel at the thermal impedance, but also at the power cycling and the reliability perspective.
Okay, thank you. So the HVD3, this targets 100 to 300 amps.
Right.
And that addresses the gap in the market. Can you explain that in a little bit more detail?
Yeah. So right now, as I said, you have the discretes, but you have the really high power modules.
Yeah.
And there was nothing sitting in between the discretes and the really high power modules.
Okay.
So one could use multiple discrete devices, parallel them, and design their own boards to achieve the similar current rating. But it's more complex. They have to add isolation, they have to add thermals, and they have to design around multiple discretes. So we're solving the problem by simplifying it within an isolated package and reduce inductance and all of that. So it solves the gap of addressing that gap between really low current and really high current.
Gotcha. Okay. So the press release describes the HVD3 as reducing the number of series connected SST modules by roughly half compared with lower voltage SiC alternatives when interfacing with the grid. Can you talk about that?
Sure. So I talked about going from grid voltage to the requirements of an AI data center server. So the grid voltage can be anywhere between 11 kilovolt to 35 kilovolt AC. Assuming you have a 35 kilovolt AC input, you have to use number of cells to achieve the ability to interface with that voltage. The higher the voltage the device you use, the lower the number of cells you can use in series. So with the 3.3 compared to a 1.2, you're able to reduce it in half because you stack 3.3 times X times 1.2 times Y.
Yeah.
So you have to achieve the similar voltage basically. So you're able to reduce it in half just comparing the 1.2 to 3.3.
Thank you. Was there any last thoughts that you wanted to share? Anything I might not have
So
asked?
in addition to the package, our customers are always asking for how do we drive the module, right?
Okay.
So you have the module, but a module without a gate driver is a car without the wheel. So we have a reference design that we released for the gate driver itself.
Okay.
So that supports this particular module. It's a fiber optic interface. So it's a two-board solution. You have your power in the bottom board and your controls on the top board. So it interfaces like a plug and play with the power module. So we're releasing this as a soft release so customers can download the design files and produce it themselves for use.
Thank you. Just a last question. I understand the BZ pack is H3 TRV certified, qualified. Will this in the future potentially be?
Right. So the BZ pack is HVAC TRB qualified, greater than 3,000 hours. We've tested the die within that package. It's clear. So the 3.3, we have the data in the die form, but we haven't tested it yet in the module. But it is in the works. But customers can use it with the confidence and the ability to know that it can pass HVAC TRB.
Okay. Well, thank you so much, Nitesh. I appreciate your time.